Good day, everyone. I will be starting this discussion by introducing to you what transport layer is and its role in the network communications. So, transport layer is responsible for the logical communication between the applications running on different hosts, and it also serves as the bridge between the application layer and the lower layers, which ensures for a smooth data transmission. The key responsibilities of transport layer includes tracking individual conversations between applications, segmenting data and reassembling it upon arrival, adding header information to segments, identifying, separating, and managing multiple conversations occurring simultaneously, and lastly, using segmentation and multiplexing to allow different communication conversations to be interleaved on the same network. These functions ensure that the data is efficiently transmitted and properly organized for the receiving application. Transport layer plays a crucial role in delivering data across the network. While the Internet Protocol or IP defines and handles addressing and routing, it does not define how data is actually transported between hosts. This is where transport layer protocols comes in. They specify how the messages are transferred between hosts or devices, ensuring proper data delivery. The two primary transport layers are TCP or Transmission Control Protocol and UDP, User Datagram Protocol. These protocols serve different purposes, which we will explore in the next slides. Let us get into the differences between UDP and TCP. So, TCP is reliable and ensures that the data is delivered accurately and in order. And some of its key characteristics include reliability, acknowledges data, resends lost data, so if a data segment is lost, TCP retransmits it. And lastly, it delivers data in a sequence order, wherein it ensures that the data arrives in the correct order. So because of these features, TCP is used in applications where accuracy is crucial, such as web browsing, email, and file transfer. On the other hand, UDP is fast and efficient, but does not guarantee delivery, and its key characteristics include fast, low overhead, does not require acknowledgement, does not reset lost data, and delivers data as soon as it arrives. And because of these features, UDP is ideal for applications where speed is more important than reliability, such as live streaming, online gaming, and voice and video calls. So, in summary, TCP is best for applications that require accuracy and reliability, whilst UDP is best for applications that need speed and efficiency.
So now I will go ahead and discuss TCP, which stands for Transmission Control Protocol. TCP is a connection-oriented protocol, which means that it establishes a connection before data transfer even begins. So, what are the features of TCP? First is that it establishes a session. TCP ensures reliable data transfer by using acknowledgement and retransmissions. Second is that it ensures reliable delivery. TCP provides error checking and flow control. Third is that it provides same order delivery, where data is delivered in the same order as it was sent. And lastly is that it supports flow control. TCP is suitable for applications where data integrity is crucial, such as web browsing and email. Next is TCP header. TCP is a stateful protocol, which means it keeps track of the state of the communication session. TCP records which information it has sent and which information has been acknowledged. shown in the PowerPoint is the TCP header, which has header fields that has its own functions. Given here are the functions of each TCP header field, which are source port, destination port, the sequence number, the acknowledgement number, header length, reserved, control bits, window size, checksum, and urgent. Now let's discuss TCP flow. The TCP flow involves a three-way handshake to establish a connection. First is SYN, where the client sends a SYN packet to the server to initiate a connection. Second is SYNAC, where the server responds with a SYNAC packet to acknowledge the request. And third is the ACK, where the client sends an ACK packet to confirm the connection is established. TCP is used by applications that require reliable data transfer. Examples include HTTP, which is web browsing, HTTPS, which is secure web browsing, FTP, which is file transfer, SMTP, which is email, and lastly, SSH. Now let's move on to UDP, which stands for User Datagram Protocol. UDP is a connectionless protocol, meaning it does not establish a connection before data transfer. The features of UDP are that UDP is faster but less reliable than TCP. Second is that data is reconstructed in the order that it is received. Next is that any segments that are lost are not resent. Third is that there is no session establishment. And lastly is that the sending is not informed about resource availability. The UDP header is far simpler than the TCP header since it only has 4 fields and requires 8 bytes, which has 64 bytes in total. Given here are the UDP header fields and their functions. First is source port, second is destination port, next is length, and lastly is checksum. Next, let's discuss UDP flow, which is pretty straightforward. First is that the sender sends datagrams to the receiver without establishing a connection. And lastly is that each datagram is independent and there is no acknowledgement of receipt. This makes UDP suitable for applications where speed is critical and some data loss is acceptable. So given here are some examples of applications that use UDP, and UDP actually uses applications that can handle some data loss but require low latency. Examples are SNMP, video conferencing or live streaming, DHCP, TFTP, voice over IP, or domain name system.
Networking is all about communication between devices, but how does a computer know which application should receive incoming data? That's where port numbers come in. What are port numbers? A port number is a 16-bit identifier used at the transport layer to direct traffic to the correct service running on a device. Without port numbers, different types of network traffic, such as web browsing, email, and file transfers, would get mixed up, making communication inefficient. Port numbers work with two main transport layer protocols: TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. TCP ensures reliable communication by establishing a connection before sending data, while UDP is faster but does not guarantee delivery. Both protocols use port numbers to track multiple, simultaneous connections on a device. One key concept in port communication is socket pairs. A socket consists of an IP address and a port number, creating a unique identifier for each network connection. For example, consider a scenario where a client with an IP address 192.168.1.5 is connecting to a web server at 192.168.1.7. The client uses a random source port, in this case 1099, while the web server listens on port 80. The complete the complete socket pair for this communication is 192.168.1.5 colon 1099 to 192.168.1.7 dot 7 colon 80. This ensures that the client's web request reaches the correct application on the server. Similarly, if the client was using FTP instead, the destination port would be 21 instead of 80. Port numbers are categorized into three ranges. The first one is the well-known ports, ranging from 0 to 1023. This is assigned to standard protocols such as HTTP, HTTPS, FTP, and SMTP. The second category is the registered port, ranging from 1024 to 49,151. This is used by specific applications such as MySQL and Microsoft SQL Server. Last but not least is the dynamic or private ports, ranging from 49,152 to 65,535. This is the temporarily assigned for client-side communication, often used by web browsers and other short-lived connections. To monitor active network connections and check which ports are in use, network administrators use the netstat command. This tool provides a list of open ports, helping identify network issues, unauthorized connection, or potential security threats. Firewalls also rely on port numbers to allow or block certain types of traffic, making port management a crucial aspect of cybersecurity. So, why are port numbers important? Understanding port numbers is essential for troubleshooting security and efficient data transmission. They enable multiple services to run simultaneously on a single device while keeping network traffic organized. Whether it's loading a page, sending an email, or streaming a video, port numbers are working behind the scenes to ensure seamless communication.
Next, we have TCP communication process, where this method uses two devices where it establishes a connection, exchange data reliably, and then close the connection using transmission control protocol. To begin, we have the TCP server processes. So each application process running on a server is configured to use a port number. So the port number is either automatically assigned or configured manually by a system administrator. So an individual server cannot have two services assigned to the same port number within the same transport layer services. Here we have a figure, the client sending TCP request, where the client 1 is requesting web services and client 2 is requesting email service of the same server. From this slide, we have two figures. First is the request destination ports, where the client one is requesting web services using well-known destination port 80 HTTP, and client 2 is requesting email service using well-known port 25 SMTP. On the other side, we have the request source ports, where client requests dynamically generate a source port number. In this case, client 1 uses a source port of 49152 and client 2 uses 51152. Next, we have another two figure. The first is the response destination ports. When the server responds to the client request, it reverses the destination and source ports of the initial request. Next is the response source ports, where the source port in the server response is the original destination port in the initial request. Moving further, we will discuss the TCP connection establishment where it focuses three-way handshake. So three-way handshake ensures that both communicating devices synchronize their initial sequence numbers and establish the necessary parameters for data transmission. So step one is synchronize where the initializing client requests a client to server communication session with the server. Step two is the acknowledgement and synchronize. So the server acknowledges the client to server communication session and requests a server to client communication session. Last step is the acknowledgement, where the initiating client acknowledges the server to client communication session. Overall, the three-way handshake shows or validates that the destination host is available to communicate, where in this example, host A is validated that host B is available. Going further, we have session termination, where a TCP connection is closed using the fin control flag requiring a two-way handshake for each one session. Terminating a full TCP conversation involves four exchanges, with either the client or server initiating the process. So we have step one, when the client has no more data to send in this stream, it sends a segment with the fin flag set. Step two is ACK or acknowledgement, where the server sends an ACK to acknowledge the receipt of the FIN to terminate the session from client to server. Step three is FIN again, but the server sends a FIN to the client to terminate the server to client session. Lastly is the ACK, where the client responds with an ACK to acknowledge the FIN from the server. Overall, in session termination, when all segments have been acknowledged, the session is now then closed. Next, we have TCP three-way handshake analysis. So hosts track data segments, maintain session state, and use TCP headers to confirm receipt. As a full duplex protocol, TCP enables two-way communication and establishes connections via a three-way handshake. So here we have a figure, a control bits field in the TCP header, or also known as flags, manages connections, especially during the three-way handshake, which includes the six bits, the urgent, acknowledgement, push, reset, synchronize, and finish, which control connection setup, data transfer, and termination. In this slide, we can see the six control beats flag, which I mentioned earlier, the urgent, acknowledgement, push, reset, synchronize, and finish. To understand three-way handshake, the function of this first confirms the destination device is on the network, two verifies the destination has an active service on the intended port, and last notifies the destination of the client's intent to establish communication.
Now, Now, I will be talking about TCP reliability and flow control, or TCP, or Transmission Control Protocol, is what ensures our data is delivered accurately and efficiently over networks. First, TCP guarantees that data packets arrive in the correct order. Sometimes, packets may get lost or arrive out of sequence. To fix this, TCP assigns sequence numbers to each packet, allowing the receiver to reorder them properly. This ensures that all data is received exactly as it was sent. For data loss and retransmission, even in the best networks, data loss can happen. TCP has built in mechanisms to detect missing packets and retransmit them. One advanced feature used today is selective acknowledgement, or SAC, or SACK. This allows the receiver to acknowledge which packets it has received, even if they arrive out of order, making retransmission more efficient. Now, let's talk about flow control. Flow control ensures that data is sent at a speed the receiver can handle. Without it, a fast sender could overwhelm a slower receiver, leading to data loss. TCP dynamically adjusts the flow of data between devices, maintaining a smooth and reliable connection. Another important concept is the maximum segment size, or MSS. This is the largest chunk of data that a receiver can accept in a single TCP segment. Typically, The MSS for IPv4 is 1460 bytes. It's calculated by subtracting the sizes of the IP and TCP headers from the standard Ethernet frame size of 1500 bytes. Finally, let's discuss congestion control. When too much data is sent over a network at once, routers can become overloaded, leading to packet loss. TCP helps manage this by using congestion control mechanisms and algorithms that adjust the data flow, preventing overload and keeping the network stable.
And lastly, I'll be talking about UDP communication, what it is, how it works, and why it's important in networking. UDP is widely used in real-time applications like video streaming, gaming, and VoIP. Let's dive in. UDP or User Datagram Protocol is a fast and lightweight communication protocol. Unlike TCP, it does not establish a connection before sending the data. This makes it ideal for where speed is more important than accuracy, such as live video streaming and online gaming. But it doesn't guarantee delivery. Some data packets may be lost or arrive out of order. One of the biggest advantages of ODP is its low overhead. It doesn't require any handshake, acknowledgement, or retransmission. This allows the data to be sent quickly and with minimal delay. However, this speed comes at a cost. UDP does not guarantee reliability, so those packets are not resent. This is unsuitable for applications that require 100% accuracy, like file transfers. Another key aspect of UDP is that the datagram can take different paths to their destination. This means they may arrive out of order, unlike TCP. UDP does not track of sequence number or attempt to reorder data. Instead, it simply delivers the packet as they are received. If the application is required of the data in the specific order, it must handle the reassembly on its own. UTP-based application use specific port numbers to send and receive data. For example, the listen and server listens on the port 53 while the radius authentication use the port 1812 when a UDP server receives a request. It forwards the data in the correct application based on the port number. In typical UDP transaction, the client selects a random source port and sends the specific data on the specific destination port on the server. For example, this in request might originate from 49,115 to go to port 53. When the server responds, it swaps the source and destination ports. This dynamic port allows the multiple clients to communicate to the same server simultaneously. Look about the pros and cons of UDP. It's fast, efficient because there's no connection setup. It requires low overhead, making it ideal for real-time application. It supports broadcast and multicast transmission. However, it does have some negatives. There is no guarantees of delivery or order. It doesn't provide error correction like TCP, and the application must handle lost or out of order data on their own. Summarize, UDP is a connectionless protocol that sends data without establishing a session. It trades reliability for speed, making it ideal for applications that prioritize low latency. Server listen on well-known ports, while clients use dynamic ports for communication. If an application can tolerate some packet loss or out-of-order delivery, UDP is the best of choice.